Hello. So this is a presentation about our report, assignment report, mathematical modeling using ordinary differential equation. Specific topic on radioactive series, potassium-40 decay. So our team members including me, Nahim Ibrahim bin Haidar Ali, matching number 215963, Muhammad Shazwan bin Shahidan 215918, Muhammad Zulhaki bin Abdul Rahim 217707710, and Muhammad Farhan bin Muhammad Sakri 215769. So I for the report I did the introduction part, so I will briefly talk about our introduction. So our introduction, ODE, what is ODE? ODE, or ordinary differential equation, are one of the types of differential equation other than partial derivative. Many people know partial derivative, but some few only, I think, even myself know about the in university days. So what is differential equation? So differential equation have a long history. A differential equation is a mathematics in mathematics is an equation that connect the derivative of one or more unknown functions. So there's a long definition there in the report. You can see about it and the history about it. So there's also a long history in the report. So Sir Isaac Newton and Christoph Bernhard Feldkirch and Gottfried Wilhelm Leibniz are the people who make differential equation come to existence. And there are also many scientists, many mathematicians who improvise the differential equation. For example, like Euler, Daniel Bernoulli, Leonhard, Jean Leron d'Alembert, and many mathematicians. So for the ordinary differential equation, there is 4 types of ordinary differential equation. First is homogeneous differential equation, non-homogeneous differential equation, linear differential equation, and non-linear differential equation. So since this is specific topic on radioactive series, I also do a short introduction in that. So radioactive series also involve ordinary differential equation. So this report focus on more potassium-40 decay, radioactive potassium isotope with a long half-life of 1.25 billion years is known as potassium-40. So the example and application will be presented by my team members. That's all for me.
Next, I will continue with the principle. So the primary process of radioactive decay is the spontaneous changes of an stable atom nucleus which produce radiation. So as a result of the probabilistic nature of this decay, no one can predict when a certain decay events will occur. However, when a vast number of atoms are taken as well, it shows statistical patterns that can be explained by mathematical models. So the concept, the penny radioactive decay, such as radioactive, decay kinetics, decay constant and activity, half-life and mean-life, decay chains and branching, decay modes, and decay energy will be covered in this section. Okay, so 2.1 is a radioactive decay kinetics. So we will get the first order decay, second order decay, and higher order decay reaction. So first order decay, the quantity of radioactive atom in isotope directly affect how quickly it decays. So first order decay is governed by the differential equation, which is dn over dt equal minus lambda n. So where n represent how many radioactive atoms they are at moment t. For the second order decays, refers to the simultaneous distribution of two particles and then the rate of decay is inversely proportional to the square of the reactant concentration. For the higher order decay reaction, three or more particles decay at once. The concentration of the reactant is related to the corresponding reaction order taken into account in the rate equation for those reactions. And then for the 2.2, decay constant and activity. For a specific isotope, the decay constant lambda is a fundamental metric that describes the rate of radioactive decay. So it describes as a likelihood that a single radioactive atom will decay during a given period of time. The decay constant, whose value depends on the particular decay process, is connected to the half-life of the isotope. So it is represented by the letter A is defined as the quantity of decays per unit of time. The decay constant can be used to compute the activity, which is A equal to lambda n, where n denotes how many radioactive atoms there are. And then for the 2.3, which is a half-life and mean-life. So half-life is the amount of time that it takes for half of the atom in a sample to undergo radioactive decay is known as the half-life of radioactive isotope. So the following gives the relationship between the half-life and decay constant, which is T half equal to ln 2 over lambda. So another measure used in radioactive decay kinetics is mean life. It reflects the typical amount of time for a radioactive atom to exist before decay. So decay constant and mean life are connected as follow: T equal to 1 over lambda. Next, 2.4, decay chains and branching. So we will have a decay chains and series overview, alpha decay chains, beta decay chains, and branching ratios and their impact on decay process. So next, I will pass to the next person.
Decay of potassium-40 is a natural process that occurs in the Earth's crust, which can be mathematically modeled and analyzed for real-world applications. Radioactive decay is a process when an unstable atomic nucleus undergoes transformations to become stable. The transformation it undergoes when decaying into different isotopes is called the decay chain, or radioactive series. Potassium-40 mainly decays through beta decay and electron capture processes. By utilizing a system of ODEs, we are able to make estimations of the age of geological samples. Geochronology is the process of determining numerical ages and dates of Earth materials and events. With potassium-40, we are able to determine the ages of rocks and minerals by constructing and solving a system of ODEs. This is done by using the potassium-argon dating method. Potassium-argon dating is a geochronology method of determining the time of origin of rocks by measuring the ratio of radioactive argon to potassium in a sample. This method has been successfully used to estimate the ages of meteorites as old as 4.5 billion years old and volcanic rocks as young as 20,000 years old. ODEs are also used in nuclear physics research, which is the study of atomic nuclei, their formation stability, and decay with the goal to understand the fundamental nuclear forces in nature, their symmetries, and the resulting complex interactions between protons and neutrons in the nucleus. Potassium-40 is of interest in this field to its radioactive properties and its decay processes. From the potassium-40 decay chain, ODEs can be used to describe the rate that the abundance of isotopes changes, which is known as decay kinetics. ODEs can also be used to extract the decay constant and use them to calculate the corresponding half-lives of the isotopes involved. Other than that, researchers are able to describe the probabilities and rates of beta decay or electron capture processes that are happening from the decay of potassium-40 by using ODEs. Another use of ODEs in nuclear physics research is to estimate the amount of heat released, the type, and the intensity of radiation emitted at various stages. These are among the many uses of ODEs in radioactive research and applications.
Hello, today I will talk about some examples regarding the ordinary differential equation and partial differential equation. So for example, regarding radioactive series, especially in radioactive decay, I will talk some examples in this video. So for the first examples, the question is remains containing 14% of the original amount of carbon-14 are found, knowing that carbon-14 half-life is tau equals to 4,730 years, date the remains. So the solution is, first we set t equals to 0 when the organism dies. Since the amount n of carbon-14 only decays after the organism dies, so we use it to create the function nt equals to n naught 2 minus t over tau, and tau equals to 5,730 years. The remain contains 14% of the original amount at the time t, so we get nt over n naught is equals to 14 over 100, which is, when we simplify it, we will get t over t equals to tau log 2 100 over 14. So from the calculation, we get the organism died 16,250 years ago. Next, the question is, a zircon sample contains 4,000 atoms of the radioactive element 235U. Given that 235U has a half-life of 700 million years, how long would it take to decay to 125 atoms? The solution is, let Q equals to mass of radioactive material at time t. So we denote it by using the equation Qt equals to Q naught 1 over 2 negative Kt. So when Q naught is equals to 4,000 atoms, T equals to 700. Qt is equals to 125 atoms. So using the equation Qt equals to Q naught e to the power of Kt, we substitute the value of Qt, Q naught, and T into the equation. We will get that the T, which is the times that it takes for the zircon sample to decay to 135 atoms, is 3,500 million years. For the next example, the radioactive isotope indium-111 is often used for diagnosis and imaging in nuclear medicine. Its half-life is 2.8 days. What was the initial mass of the isotope before decay if the mass in 2 weeks was 5 grams? So first of all, let Q equals to mass of radioactive isotope at time t. When t equals to 214 days, Qt is equals to 5 grams. So the half-life is 2.8 days, tau equals to 2.8 days. We use the equation K is equals to ln 2 over tau, which is we'll get K is equals to ln 2 over 2.8. So we use the equation Qt is equals to Q naught e to the negative Kt. Then when we simplify it, we will get Q naught is equals to 5e to the power of negative 14 ln 2 over 2.8. So when t equals to 810, we will find the Q naught is equals to 4e to the power of 810 ln 2 over 1620, which will just substitute the value of t into the equation. So for the final answer, we will get Q naught is equal to 2.83 grams. So that's all for some of the examples regarding ODE and VDE in radioactive series. So thank you.